In this chapter, we will discuss distributions, also called generalized functions, that were introduced by Laurent Schwartz, who was a Fields Medal in 1950 and who also was a university professor in a nearby institution, Polytechnique, actually just across the street from here. We will also discuss Sobolev spaces, named after Sergei Sobolev, also a mathematician from the 20th century. Let me explain what we are trying to do when we do distributions and why is distribution important for you and for the rest of this class. Let me consider some functions. Basically, all the functions I will consider here are locally integrable L1 log, which means that I can integrate them on any compact set with no problem. So I just, gave a few of them here, obviously not write them all. X gives x squared plus sine x, absolute value, etc. Now, the question is, can I differentiate these functions? Well, some of them I can. I mean, x squared plus sine x, obviously the derivative will be in L1 log. Actually, it's written right there. But what about the absolute value? What about the function that is equal to -1 if x is negative and 1 if x is positive? Well, these functions will not be differentiable in L1 log. I mean, we could differentiate them in some parts of R, but not as a whole. So what I'm saying is these functions cannot be differentiated in L1 log. But what happens if I want to differentiate them? What if I want the derivative? Well, as we said, it's not differentiable. So wanting the derivative for these non-differentiable functions is like walking in a restaurant and asking for a vegan T-bone. Well, it's not going to happen. So what can we do? I mean, we have non-differentiable functions in L1 log, which means that we cannot differentiate them. Or can we? Maybe we could differentiate them, but the derivative would be in a bigger set, in something that is not L1 log, that is not even a function. Take, for instance, -1 on R minus and 1 R plus. Well, maybe the derivative is in a bigger set. It's not a function. Okay, before we go any further with functions, let me talk about something that has nothing to do with functions, nor with distributions. I would like to talk about real numbers. So let's consider real numbers here, and forget about the distributions for a minute, or the functions. And these numbers, obviously, 4 has a square root, which is 2. Actually, it has 2 square roots, 2 and -2 in R. And 2 has also 2 square root, and negative square root of 2 and square root of 2. But what about -4? Well, -4 has a square root, you would say, but not in R. And same thing for -1. Actually, the square root is, or has to be in something bigger, because obviously if you take any real number, if that real number is positive, plus by plus is plus, so the square will be positive, and if it's negative, minus by minus is plus, so it will also be positive, which means that you have absolutely no chance, as you know, to take the square of any real number and find -4, or -1 for that matter, of -1/3. So, so that's where you decide to do, okay, let me consider R square, right? Basically the set of couples, ABs, right? And you say, okay, every real number can be injected in R2 with the application X gives X0, right? You have a couple, X, AB, and X becomes X, and then you add 0. So I'm saying that this application J is injective. And I can define on R2 a plus and a multiplication. Let me define plus. So AB plus A prime B prime is A plus A prime and B plus B prime. And I can define this operation if I want to. And I can define a multiplication. AB times A prime B prime is AA prime minus BB prime for the first component of the couple, and AB prime plus A prime B for the second component. All right. As you can see, if I look at what happens for the all these couples that come from R, in other words, the x zeros, right? If I do a0 plus a prime 0, well, that is going to be a plus a prime 0. Okay? In other words, what I have is that j of a plus j of a prime is j of a plus a prime. And for the multiplication, if I do a0 times a prime 0, well, then I just apply this a prime minus bb prime, ab prime plus a prime b, and what I get is a prime 0. So what we have is j of a times j of a prime is j of a plus a prime. So what we're saying here is that the plus and the multiplication that I define on R2 somehow applies to R, or actually to the elements coming from R, in just a very standard way, the way we usually use plus and multiplication. But what is interesting is what happens if I do 0, 1 times 0, 1. Now what happens then? Well, then a is equal to 0, b is equal, a is equal to 0, b is equal to 1, a prime is equal to 0, b prime is equal to 1. So, well, then that means the first component is a prime minus bb prime, that's going to be minus 1. And the second component is going to be ab prime plus a prime b, that's 0. So what we're saying is that 0, 1 times 0, 1 is minus 1, 0. All of a sudden we have a number that when it's squared gives me minus 1, 0. And same thing, of course, for minus 4, 0. 0, 2 is going to be squared into minus 4, 0. Actually, we're going to have two numbers that have this property, so two square roots for negative 1, 0 and for minus 4, 0. And on top of this, R square equipped with plus and multiplication is a field. Okay. Well, let's actually call the 0, 1 I, and what we have is I times I equals minus 1, 0, which basically we want to call this minus 1. Actually, instead of AB, which is kind of a cumbersome notation, let's actually, instead of AB, let me note this, A plus IB, since I is 0, 1. And I just rewrote exactly what I wrote before. I just replaced every AB by A plus IB and R2 by C. C plus multiplication is a field. And what basically we're going to have is dropping the 0i, which actually is cumbersome for no reason. And here's what we have. So we have R, which is injected in C. And because it's injected in C, let's actually identify all the real numbers with their counterpart in C. And let's just write that R is included in C. Okay? That is, you know, what you did before, right? I mean, I'm not saying this is anything new. You've done this before. What I'm saying is we're going to use this trick again today. We're going to use this trick on functions that cannot be differentiated in L1 log, and we're going to take a bigger set and differentiate these functions there. Okay? That bigger set will be called D prime. Its elements will be called distributions. And that's what we're going to do in this chapter. We're going to define this set D prime. That will be the first two videos we'll watch. Then we'll actually work on some operations on the distributions. We'll actually define operations on the distributions. And then we will discuss Sobolev spaces, which is a nice thing to do once you have distributions. So to define distributions, we'll basically define the set of distributions D prime. And then we will see that some functions, basically the functions in L1 log, can be injected into D prime, and the set where they injected, basically the image of L1 log, will be called the regular distribution. So basically L1 log functions will be considered as regular distributions exactly the same way as real numbers are considered as the real line in the complex plane. Then we will work on some operations for the distributions. We'll define the sum. For the product, it won't be the product of distributions, it will be the product of the distributions with a C-infinity function. We'll get back to this in that video 2.1. And of course, we will define the derivative of the distribution because that's exactly why we have distributions to begin with. Now, there is something we could have done, and we're not going to do it because of time, but you can really do it by yourself if you're interested, especially after the CIP class you just had last semester. It is to define the Fourier transform of a distribution. That is interesting because it allows you to bridge the gap between the Fourier transform of a function in L1 or L2 and the Fourier series for periodic functions. So it's quite interesting, and I will put a link on the website so you can actually look at what it means, but it's not technically part of this class. And you can also define the convolution product of two distributions, but there are a few tricks because you have to talk about the Schwartz space, so that's also a little bit complicated, or actually not in the scope of this PDE class. But again, if you're interested, and I hope you are, you can actually look at this as well. All right, so after we have defined these operations on distributions, in other words, generalized, extended these operations from L1 log to D prime, we will discuss Sobolev spaces. 3 videos for this. We will define Sobolev spaces, HK, talk about their regularity, talk about the trace theorem and integration by parts, and we'll end this chapter with defining the space H1, 0. All right, well, throughout this chapter, I will be a non-empty open interval of R. That means AB or A plus infinity minus infinity B, or R itself, A being obviously A being smaller than B and being two real numbers, obviously. And to finish this introduction, I would like to point out that even though we are working in R, we could extend these definitions and all of this work to Rn.